thanks. This is a perfect setup. So let's see. So I'm going to talk a little bit about what it takes to make the blockchain kind of more usable for business. I'm a cryptographer, so to me, everything looks like a crypto problem. And so let me tell you a little bit about the beautiful problems that come up from these blockchain technologies. I can't give a talk on cryptocurrencies without talking about the huge increases in prices over the last year. I actually think this is a bad thing for the research community because it's causing overhype in the area, and it's causing the research community to miss out on the beautiful open problems here. And this is an area that, like I said, suffers from a lot of overhype, but there are really new scientific problems to think about here. So again, I'm a technologist, so I'm interested in the computer science aspects of these problems. So these blockchains, they generate questions about new consensus protocols, new programming languages for smart contracts. So ways in which we can write smart contracts in which we can verify that the contracts do what they're supposed to do. There have been many famous mistakes of smart contracts that end up not doing what they're supposed to, and millions of dollars, actually tens of millions of dollars, are getting lost as a result. The DAO is a typical example of that. There's new cryptography that's needed for these blockchains, and finally, there's lots of mechanism design questions. I'll just throw one out there. So we talked about miners and how they operate. I think you guys need to understand that miners today, they're not like people sitting in their homes and mining. That doesn't work anymore because of the expense of what it takes to mine. So miners are actually large organizations today that have thousands, if not tens of thousands of machines doing the mining. That's one type of miner. The other type of miner is a mining pool where 100,000 people kind of come together saying, well, each donate cycles to mining so that we get the block reward. And then the question is, how do you distribute the block rewards across the people who contribute to the pool? That's actually a really nice mechanism design question. So might be interesting for folks here to think about. Yeah. So even though my machine participated but did not generate the winning solution, I should still be eligible for some of the reward. And the question is how to distribute those rewards. So anyhow, in this talk, I'm going to focus, of course, on the crypto aspects, and I hope I'll convey that there's lots to do here as well. But this area, as I say, even though it suffers from overhype, this area is going to be with us now for a long time. This is a wonderful scientific research area. And if at your institutions there are new people working on blockchains, you're really missing out, because this area is going to be with us for a long time. All right, so let's continue. So I wanted to say a few words. So thanks for the setup explaining how Bitcoin works. I wanted to say a few words about Bitcoin, although everything that I'm going to say is much more generic and applies to almost all cryptocurrencies out there. So, but I'll pick on Bitcoin as an example. So of course, the Bitcoin blockchain is a chain of blocks. Yeah. So you can see these are the block headers that live in each block. What lives in the block header is basically a hash of the previous block. This is what causes the chain. There's also a set of transactions. The transactions themselves are organized in a tree for a certain reason, which I won't get into here. Then there's a nonce, which is related to the proof of work, and then there's a timestamp as to when this block was actually mined. The timestamp is also used for updating the hardness, the proof of work hardness, as was mentioned before. Okay, so that's what the blockchain looks like. And when we zoom in on transactions, I just wanted to emphasize how the actual model works. So there's no accounts and no account balances in Bitcoin. The way money is managed is through what are called unspent transaction outputs. So every transaction has a bunch of inputs and a bunch of outputs. Whenever a transaction is created, what is created is what's called an unspent transaction output, a UTXO. So this would be UTXO number 1 and UTXO number 2. The UTXO basically has a value associated with it, which is how much money was transferred to this address. And similarly here, how much money was transferred to this address. So how many coins were transferred to this address. And then a subsequent transaction, all it does is it points to a previously unspent transaction output as part of its inputs. And then the process repeats. We create new UTXOs. The point of a UTXO is it can only be spent once. So once a UTXO has been spent, it can no longer be spent again, and you might as well forget that it ever existed. And in fact, most miners will delete the UTXOs once they've been spent. So the only thing that the miners have to keep in memory is what's called the UTXO set, which is the set of all unspent transactions on the blockchain. Everything else, everything that's been spent, is erased and does not need to be kept online. Is that clear? So that's the UTXO model. So there are actually no balances or accounts or addresses or accounts. It's all managed by UTXOs that bind values to addresses. Okay, so that's the UTXO model. The problem with this is this model is completely unfit for business. Yeah, it's a complete mismatch for business. And so I just listed an example transaction here. So what you see in this transaction is the following. You can see that these two addresses, these two Bitcoin addresses, each contribute this amount of Bitcoin. And they go to these two addresses. And the output is, this address got 2 Bitcoins, and this address got 0.01 Bitcoin. And in addition, the fee was 0.0179 Bitcoin that goes to the miner. The problem with this is when you look at it, you realize, wait a minute, these addresses are completely public on the blockchain, so I can tell exactly who is paying who. So to you, this might seem a little bizarre because this address is just a cryptographic hash. So how do I bind this to a physical entity? But it turns out, actually, there's a lot of work that shows that, in fact, it's very easy to bind these addresses to actual physical entities. Just to give you an idea for how this works, if you pay me in Bitcoin, let's say my address is the output address, and then later on I go and spend my Bitcoin at a coffee shop on the Stanford campus, boom, boom, you just learned that whoever was paid here is someone who probably works at Stanford. The next thing is, I might end up, maybe I spend some money, some Bitcoin on buying coffee on the Berkeley campus today, and then you surmise, oh, probably he's attending a Simon's workshop today. And very quickly, you can kind of nail down exactly who this person is. And there's been a lot of work on this, on basically unmasking who these identities are and binding them to physical addresses. In fact, there's a bunch of companies that do this. And so, you should not assume this is what's called pseudonymous addresses. They look random, but in fact, they're not too difficult to bind to real world addresses. Okay, so that's one fact, that it's easy to tell who's paying who. The bigger issue is that, in fact, the amounts are completely public on the blockchain. Now, if you think about that, that doesn't make any sense for businesses. This is just immediately prevents businesses from using the blockchain for payment. Just think about if everyone knew how much was being paid to who, that means, if Stanford paid my salary in Bitcoin, anyone can look on the blockchain and see exactly what my salary is. That makes no sense at all. Maybe in Berkeley it makes sense. Public university. At Stanford, that does not make sense at all, right? And more generally, in industry, this would not be acceptable. But even more generally, if you want to manage supply chain using the blockchain, right? If you can look on the blockchain and see exactly how much Ford pays its supplier for tires, that would violate basically all the rules of doing business between customers and suppliers. So this is kind of just a mismatch. Fundamentally, the blockchain is a mismatch for business. Yeah?
Generate a different identity anytime you want?
You can, but in fact, it's not that difficult to link all these identities together. Yeah, so like I said, there's a lot. I'm not going to talk about privacy on the blockchain. I can tell you, by now there are dozens of papers and companies that all they do all day long is just analyze the blockchain and bind identities to say all these addresses actually belong to one identity, and then you can match the identity to a physical entity based on where the addresses are. Yeah, it's not that hard. There are lots of algorithms. It's actually pretty interesting graph algorithms. But with enough graph algorithms, you can actually do it. Okay, so there's a problem clear. So payer and payer are public. And more importantly, the values that are being transferred are public as well. So there's a system called Zcash and Monero that actually tries to hide who the payer and payee are. In this talk, I'm actually not going to talk about hiding the payer and payee. I'm more worried about hiding the value, which is essential, again, for businesses. So the payer and payee will continue to be public. I just want to hide what values are being paid. So you'll know that I'm a Stanford employee and Stanford pays me a salary. You just wouldn't know what the salary is. OK, so let's talk about how we do that. So the idea, actually, this is an idea that dates back to 2016 due to Greg Maxwell. So the idea is to basically change how the blockchain operates. So instead of writing values on the blockchain, instead of writing these actual numbers on the blockchain, what we're instead going to do is we're going to write what are called commitments. Okay, so what are commitments? Well, so I can't give a talk without doing a little bit of math. So what are commitments? Commitments, you can think of it as taking a number and sticking it in an envelope and then putting the envelope on the blockchain. So I'm bound to that number, but nobody can see what that number is. It's in the envelope. And mathematically, the way this works is what I do is I kind of give you this number here, which is essentially the value is embedded in this exponent, and it's being blinded by some random number that's multiplied in, so that overall this number reveals nothing about the value v, but I cannot change what the value v is once I commit to it. Okay, so that's what's called a cryptographic commitment, and that's what we're going to put on the blockchain. Okay, so now if you look at the transaction, you have no idea how much was transferred. All you see are just these cryptographic hashes, which mean absolutely nothing to you. The transaction fee, by the way, continues to be public because the miner needs to collect it. Yeah, so we're not hiding transaction fees either. Okay, good. So now that's a fine idea, but now you immediately run into a big problem. Yeah, so you think about doing that. The problem now is, if you look at the blockchain now, how do you verify that the transaction is valid? If you don't see the amounts, how do you know the transaction is valid? So what does it mean for a transaction to be valid? Well, fundamentally, what we'd like to make sure is that the sum of the inputs is equal to the sum of the outputs plus the fee. Right? That's kind of the fundamental equation of a validity for a transaction. But now you can't do that. You can't verify that it's true. So we just lost the whole point of a blockchain. Right? The whole point of a blockchain is anyone can look at it and verify that everything is valid. And now we can't do that anymore. So what do? Yeah, so how do we verify this equation? And the answer is, crypto magic. Yeah, so the crypto magic is what? Anybody know? No, not that magic. Slightly different crypto magic. So the crypto magic here is zero knowledge proofs. Okay, so it's homomorphic's brother. Yeah, so or sister rather. So zero knowledge proof. Yeah. So what are we going to do? Essentially, when we create a transaction, what we'll additionally create a zero knowledge proof that says that this equality actually holds. And it turns out that's actually not very difficult to do. Yeah, and because of the way these commitments work, it's actually quite easy. This is a linear equation, and it's quite easy to produce zero knowledge proofs for a linear equation. I should say zero knowledge proof means that I can convince you that of a fact that is true without revealing the underlying values. So you'll be convinced that star holds, but you wouldn't know what the input values and output values are. Okay, so that's number one. However, there's another requirement which we almost ignore. And the other requirement is that all these values, these inputs and output values, all have to be positive. In fact, they all have to be positive in the interval 0 to 2 to the 52 minus 1. This is basically the unit of spending in Bitcoin. Yeah? So the numbers have to be positive. Think about that. If the numbers were not necessarily positive, we would run immediately into a problem. Right? If one of these outputs happened to be negative, then here's what I would do. I would create a transaction that takes, say, 5 Bitcoins as input, and then outputs one UTXO worth 7, and the other UTXO would be worth -2. Yeah, so star is satisfied. However, now I have a UTXO that's worth 7 that I can go spend wherever I want. So I just created 2 Bitcoins out of thin air. So the idea that this requirement to prove that things are positive is absolutely fundamental to preventing spenders from creating money out of thin air. Yeah, this is essential. Even though normally we would ignore it, this is kind of a necessary thing to verify. Yeah?
One question I had is, you said that the fees are still publicly visible.
Yeah.
I presume there's some correlation between fees and transaction values, or is that not true?
No, there's no correlation. So the fees are determined by how quickly you want the transaction to be processed, and also there are some transactions that happen to be bigger because they have more inputs and outputs. Transactions that are big, if a miner takes a transaction that's bigger, that means he has less space in the block to. He can only package fewer transactions in the block because. So he has to be compensated. So if the transaction is like twice as big as a normal transaction fee has to be twice as big. Otherwise, the miner wouldn't want to take it, because it would cost them. There would be a cost to that. So in fact, everything that was said before is correct. I mean, the transactions are packaged based on their value, modulo the size as well. So there's actually a bit of a bin packing problem when you decide which transactions to take. Yeah. Okay, so there's the problem clear. So we have to prove star, and we have to prove that things are positive. It turns out proving linear relations is easy. Proving that things are positive is hard. Yeah, and that's actually where our work is. And so what we did is basically we have a new system called Bulletproofs, which is a way to actually do these zero-knowledge proofs very efficiently. Yeah, efficient zero-knowledge proofs on committed values. So you can prove that the committed value is positive. I can tell you that our proof size, if you have an n-bit range, our proof size is logarithmic in n, where previously it was linear in n. So this new Bulletproofs actually is an exponential improvement on what was known before. Which, I don't know, it's kind of amazing. It's a little surprising that it can be done. I should say it's built on an earlier proof systems of Boodle et al. The more important thing is, typically in the blockchain, you don't just have one zero-knowledge proof. You have many zero-knowledge proofs. Yeah, and in fact, if you need to do d-range proofs, you need to prove that d values are positive. Because of this logarithmic behavior, before it would be the size of the proof would be d times n. For us, it's log n plus log d. So if you need to do 10 proofs, you just add 3 more elements, and you have 10 proofs. Yeah. So this is a big deal. This is kind of a very, very large savings on size for the blockchain. So let me show you this concretely how well this works. So here we have kind of if you need to do one proof, range proof for the blockchain. Originally the proof would have been 4 kilobytes. With us, there's 672 bytes. But if you need to do 10 proofs, in other words, if you have or 2 proofs, if you have 2 outputs, before the proof would just double in size, whereas for us it's just an additive. You just add a little bit, one more element to the proof and everything, and you have 2 proofs basically. Similarly, if you need to do 10 proofs, if you have a transaction with 10 outputs, before it would become really quite expensive to include, whereas for us it's actually relatively cheap to do. I wanted to mention also there's another technology for zero-knowledge proofs called snarks, but that actually has slightly different trade-offs. So I think in the interest of time, I will not talk about snarks here. Okay, so that's kind of where we are. So just to conclude, I wanted to tell you that essentially what we're able to do, so we're able to basically make Bitcoin transactions usable for salaries, for supply chain, and things like that. And then basically because our proofs are so much shorter, we can reduce the blockchain size by almost a factor of 9. So it's a lot of savings for the miners. It reduces costs for everybody basically. What's even more interesting is we have an older result on proving solvency. So you must have heard of exchanges that, so the idea in cryptocurrency exchanges is rather than people keeping the money at home themselves where they could, lose them. Say your house catches fire and now you lost all your money. You give the private key to an exchange like Coinbase to manage. Well, some people gave their secret keys to an exchange called Mt. Gox. And that hasn't turned out so well. Yes, Mt. Gox sort of lost all the money that was given to them. So we have this mechanism, which is a zero-knowledge proofs of solvency, where the exchange can do something that cannot be done in the physical world. An exchange can prove that the sum of its obligations is less than or equal to the sum of its assets, and it can do so at zero knowledge, so it doesn't reveal what its obligations are, and it doesn't reveal what its assets are. Yeah, so we can do all that. And with these new bulletproof techniques, actually, we kind of get like a 300x improvement over our previous protocol. So yeah, so this seems to have lots of applications to various blockchain requirements. And finally, I was really happy to see Monero is one of the privacy mechanisms, private blockchains, and they just announced that they're moving to bulletproofs. So this presumably this summer will get deployed. So it's kind of cool actually. This space, like you come up with an idea and people quickly run with it, which is really, really, really fun to which is why it's really fun to work in. So again, I encourage everyone, to work in the area. There's a lot of open problems, lots of fun problems to work on, and people are kind of desperate for ideas. So anything you come up with, people will adopt. Okay, so I'll stop here. Thanks, and move on.
Thanks. While the next speaker is setting up, there's time for 1 or 2 questions. But open problems.
What?
Open problems.
Well, look, in the consensus space, there's still lots of questions about consensus protocols. So this proof of work consensus, or rather mining on the longest chain, is problematic for many, many reasons. Yeah, it means if you have, like mining on the longest chain means that if you have a really large transaction for like $1 billion, it's quite dangerous to do on the blockchain because if I could
spend the $1 billion, and then I could actually offer someone a reward to fork the chain, right? So that's, they'll lose everything they've gained so far, but they'll gain this huge transaction that was just created. So mining on the longest blockchain actually is kind of problematic for large transactions. So how do we handle that? And that's, again, lots of ideas for how to handle that properly, but there's still a lot of need for more. There are a lot of open problems around languages for smart contracts. How do we write smart contracts in a way that we can verify them efficiently? So that's a huge area. And even in mechanism design, like I said, like these mining pools, we still don't have a good answer. So lots to think about. Cool, thanks.
Thank you.
All right.
Any
All
other
set?
questions?
Set, thank you.
Yeah.
Yeah, so next speaker needs no introduction, Professor Bulletproofs on real-time decision.